is fine. I
Okay, good.
think.
All right, we still got 15 minutes or so to go, I guess.
Yes, yes, about 50 minutes. It's early in the morning. I think it's before 8.
Yeah, not too bad though.
Okay. Okay. Thank you for spending your morning with us. Yeah, I
Yeah,
I wi- I wish that the discussion worth your time.
yeah, in the past this would have been early for me, but now I have dogs who always get up by this time. So we've
How
already
early?
been we've
How
already been
early?
out for a walk, so I'm used to being up now.
Okay, okay. How many dogs you have?
Two dogs.
Two dogs. And how early they get up?
Uh, they got up about an hour ago.
Oh, an hour ago. Okay.
Yeah.
Great.
you in a meeting? Plug it into the bank and use the debit card. So that's fixed.
Okay.
We, we, we can start whenever you're ready, Professor.
Okay.
Okay. So welcome everyone, and welcome, dear Professor Norvig, for accepting our invitation. It's truly an honor. I think in Sharif, you don't need any introduction. We start learning about AI from your great book, and it shaped our view about how to think about intelligence. So without further ado, I'm gonna hand it temporarily to my dear professor, Professor Rohwan, to welcome you on his side, and then we can have your great talk.
Thank you.
Hi, Peter.
Hi.
How are you?
I'm good. Happy to be here. Sorry, I'm not there in person, but this is next best thing.
Great, great. My name is Mohammad Rohman. I am the lecturer of this course, Reinforcement Learning, which is a graduate course. And I'm very pleased to have you today. I'm looking forward to hear your talk.
Thank you.
Sure. So let's, whenever you're ready, I would be happy to hand it over to you to start your talk.
Great. Well, thank you, everybody. I'm sorry I can't see you, but I hope this goes well. So I want to talk about the future of AI and programming. And first, starting off by saying, where are we at the current point in time? And there's a bunch of tools that are available, and you can use them, and you can actually make stuff that works. And so Andrej Karpathy, one of the leaders in the AI field, a year ago, or a year and a half, I guess, said the hottest new programming language is English. And that was in 2023. And then in 2025, he invented this term vibe coding, of saying, well, you don't have to think about the code anymore. You just start saying what you want, and the system writes code for you. So we've come a long way in 1 year. In 2023, when he said that, it was interesting, but it didn't really work. And now, for a lot of things, it does work. Now, part of the reason it works for Andre is that he's an expert. He knows how to program. He could have done it himself. And so when he gives a prompt, he knows exactly the right prompt to give, both in terms of the external view of what is it the program should do, and also the internal view of how should it do it. And he says that when the code comes back, he doesn't really look at it, but he knows enough that if it comes back and there's something wrong, he can just kind of smell that there's something wrong and then update the prompt without having to read it line by line. So it's great that it works for people like that who already have the expertise to make them better. But what else can it do? Now, here's Terence Tao, and he's talking about using AI models to help doing mathematics. I think Tao is the world's greatest living mathematician. And he says the experience of using these tools is roughly on par with trying to advise a mediocre but not completely incompetent graduate student. And again, he says this is a huge advance over just a year ago. So we're making a lot of progress. Now, I want to talk about this problem. So this is from way back in 2022, and DeepMind released AlphaCode, which solved a bunch of problems in what had previously been a human programming contest. And here's the one particular problem that they decided to highlight in the paper describing what they had done. It's called the backspace problem. And I'll just describe it briefly here. the idea is that you're given two strings, S and T, and you're asked to figure out, is there a way to type the letters of S, but replace some of the characters with a backspace character such that the output is T? So the first example is if the input S is ABABA and you're trying to create BA, one way you could do it is replace the first three characters with backspaces and then just type BA. So you're asked to do that. Here's the code that AlphaCode came up with, and it's definitely correct. It solves the problem and gets it completely right. But here's my code review for the problem. All right, and so there's a lot of things there, and basically, uh, I don't think I'd let a single line be checked in to my repository. Kind of throughout it, there's just stuff going wrong. And so I won't go through every one of them, but one in particular I want to point out is right in the middle here. I'm not sure if you can see my cursor, but below the top red dotted outline, it initializes a stack called C to the empty stack. And then when it goes into the while loop, every time it pops something off of stack B, it saves it onto stack C. Now this kind of makes sense, right? So if you're familiar with lots of programs, you've seen this idiom before. You pop something off one stack and you want to save it onto another stack. But it turns out that C is never used anywhere else in the program. And I've seen programmers who do things like this. Oh, we better save this element of B just in case we might need it later. And I don't want these kinds of people to be touching my code base. So that's where we were in 2022. It could get it right. It wasn't the most efficient program. It didn't have good style. It had some weird stuff in it, but it was sort of at a par with human programmers in terms of the number of things it could get right. But also a lot of things wrong. And maybe it shouldn't be surprising that there were a lot of things wrong, because after all, it was trained on a bunch of code written by everybody on the web, and half the programmers are below average. So it was trained on that. Now, here's what I would have liked to see, and I wrote this back in 2022. So one thing I'd like to be able to do is ask the system, write me a bunch of test cases and have it automatically come up with those. And I'd like to say, show me a really slow program, but one that's so short that it's obviously correct, and then show me how the program you write, the efficient version, can be arrived at by transforming this slow but correct version. And I'd like to be able to have a conversation, so sort of as if I was doing pair programming, and sort of answer all these questions here. I won't go through them one by one. So that's what I'd like to see. That was not available at all in 2022, but today in 2025, it is. And so I asked this question again in 2025 to Gemini. So AlphaCode was specifically trained on programming examples. Gemini is broader, is not aimed at programming. It's trained on everything on the web, and yet it gives a very good answer. There may be a few tiny little stylistic quibbles, but basically this is really good code. It's very efficient. It's efficiency of order n, whereas the previous one was order n squared. And I don't show the discussion, but there is a discussion of essentially all the things that I said that I'd like to see. It came up with automatically without me even asking for it, right? So we're a lot better off in 2025 than we were in 2022 or even in 2024. Here's another example that I played with. So there was a lot of discussion of the idea of theory of mind for large language models. So what does that mean? So theory of mind means, can the language model think about not only what it knows, but also think about what other people knows and the difference between what it knows and what somebody else knows. And so I asked it to solve this logic puzzle called the Cheryl's birthday puzzle. And it has that kind of idea in it that you don't know as the puzzle solver what each of the characters knows, right? So in this puzzle, there's a setup, and then Albert says, I don't know when Cheryl's birthday is. And then Bernard said, well, after you said that, now I know. So his reasoning about Albert's state of knowledge helped him to know. And then Albert says, well, now I know too, after reasoning about what Bernard knows. So it's a well-known puzzle. There's a well-known solution. And I asked these LLMs, 9 different LLMs, to write a program to solve it. And in 2024, none of them could do it. And they were all confident, and they wrote a program, and all the programs were wrong. And in 2025, 3 of the programs came out right. And the other ones are not quite there yet. So that's asking them to write a program. And I also asked them to just reason it out. And again, in 2024, none of them could do it. They knew the original puzzle, but when I changed it around and asked it to solve a different puzzle, couldn't do that. And in 2025, half of them could do it properly, right? So a lot of progress just in the last year. And I think what's happening here is there's this idea of threshold models in technology transitions. And so that's the idea that things start getting better and better, and then they reach this threshold, and it makes a big difference. And I worked on speech recognition at Google going back for, I guess, 15 years now. And for a long time, we felt like, well, we're doing pretty good. You know, we're getting a couple percent better every year in terms of word accuracy, but we're still not seeing a lot of customers. There's early adopters who like it, but the general public isn't using it yet. And then all of a sudden, we hit this level that it was good enough, and then everybody started using it. And so it was nonlinear sort of inaccuracy. You had to reach this point where the annoyances of getting things wrong were less than the benefits of using it. And then all of a sudden, everybody started using it. And it feels like we're right there at that point in terms of using language models for programming. So how do we get here? Here's a great quote from Abraham Lincoln. I agree with him. He says, the written word may be man's greatest invention. It allows us to converse with the dead, the absent, and the unborn. And I agree that's exactly right. Now, in some sense, you might say, well, the spoken word came first, and that's most important. And the spoken word kind of enabled civilization. It allowed larger groups of people to get together and exist with each other and prosper. But the written word allowed us to pass things down through generations. And so that's really what enabled technology to flourish. Now, I got to say, I've been at this a long time. I'm an AI hipster. I was doing it before it was cool. I started trying to get computers to understand language in 1980. Been trying ever since. And back then I thought, yes, there's something on the written page that we have to understand. But most of the hard part is going to be what's going on inside the head when you read something. And that's really what we focused our research on. And now with large language models, we kind of find out, well, you didn't need to do too much to understand what's going on in the head. You just had to set up a neural net model that has the right level of flexibility to learn from the data. And then you just give it trillions of pages of data and it works. And in 1980, it didn't work because we only had thousands of pages of data, not trillions. And even training on 1,000 pages of data didn't get you anywhere. But when you have enough words, it just works, right? So we're really going back to the invention of written language around 3000 BC to the current day. That's what's made all the difference. So that's natural language. And natural language was defined specifically to be able to do this. But is code, our programming language, is different than natural languages like English or other natural languages. Now, one of our most famous computer scientists, Edgar Dijkstra, said, in the discrete world of computing, there's no meaningful metric in which small changes and small effects go hand in hand, and there never will be. And that makes sense, right? So if you can't quite hear me and you miss one word of what I'm saying, you can still figure out from context what's going on. But if you flip one bit in a program, it could ruin the whole thing. And if that's right, then what we use in AI, this idea of gradient descent, of you make small changes and you get small improvements and you keep on doing that until you minimize your error, that's not going to work. So if Dijkstra's right, then we can never do programming with large language models. Now here's another luminary, Arthur C. Clarke, who says, when a distinguished elderly scientist says something is possible, he's probably right. When he says it's impossible, he's probably wrong. So we've got two sides of the argument here, and I'm going to go to a third luminary, one of the inventors of Unix, Ken Thompson, who said, when in doubt, use brute force. And we've got the brute force to do this. We've got the GPUs and the other kind of processing, and we can do it. And it turns out Dijkstra was wrong. So yes, there are programs where if you flip one bit, it makes a big change, and it's hard to differentiate over that. But most of the programs aren't like that, and you can just avoid those ones and find some other program that's at a minimum for the error surface. And so it just works. So I'm going to talk about the who, the what, the when, and the how of using AI for software development. So who? So there's a lot of changes going on. I think smaller teams are going to be able to do more. Experts are going to be better at what they do, like Andrej Karpathy. But more interesting to me is non-programmers are going to be successful. So the end users, the managers, the people who are, a scientist who's expert in the subject, but is not a programmer, or the semi-technical people, they're going to be able to do a lot. So we're really going to be democratizing coding and bringing it to more people and more use cases. Here's an example, Makoti Koke. So he's an engineer, and his parents have a cucumber farm, and he was kind of saying, I don't want to get stuck having to manage this cucumber farm when my parents get older. So he built a computer vision system to classify cucumbers. And he didn't know that much about it, but he took the tools that were available and just kind of assembled a vision system so that the cucumbers come by a conveyor belt and they all get sorted into the right categories. And then he didn't get stuck having to be a cucumber farmer for the rest of his life. So it's great that he was able to do that. And just a few years before, it would have taken an expert team of researchers in computer vision to be able to do this. And now he's not a complete novice. He had some technical skills, but no expertise in either computer vision or cucumbers, and he was able to put this together. Now, just as an aside, there's an XKCD comic for everything. So just point out, if you do something yourself, you could always say, I trained a neural net to solve this problem, since you yourself are a neural net. Okay, one more example. So this is Professor Ethan Mollick in the business school at the Wharton School at University of Pennsylvania. And he built a simulation for his students to be able to go through the process of having a startup and seeing if it succeeds or fails. And so again, he's a professor, he's a sort of a technical person, but not a professional programmer. And yet he was able to build this simulation game that was very useful to his students because of the help of AI. And without it, he could have hired a professional programmer to do it, but he never would have tried himself without the help of AI. And I think there'll be a lot of more cases like that, where people know something and they can say, I want to be able to do this. Okay, so when? So part of the point we've seen so far is 2025 seems like the right point, and before 2023 definitely was the wrong point. Seems like everything's going faster. Is going to be kind of just in time, that you can say, I want to do this new thing that I never tried before, and I can start doing it right now. So that's all great and promising, and feels like we're right on the edge of making progress. One thing I've got to say that we're far away from is being able to do this in real time. So there's a big difference between asking a question and waiting seconds or even a minute versus getting something back at 100 milliseconds. If you get it back in 100 milliseconds, you're in the flow, it hasn't interrupted your train of thought, and you can keep going rather than kind of taking a break. And that's what traditional tools have been able to do, right? So if you look at like the autocomplete you have in your IDE, that's got to come back within 100 milliseconds to keep you in the flow, and it does. But these AI tools, they aren't at that level yet. And so I think it'll be interesting to say, what is it that we want to get within that 100 millisecond time frame to keep you in the flow versus what is it that you can wait 10 seconds, 20 seconds, and have it be worth your time versus what is it maybe you can wait an hour or even overnight to get a bigger chunk of work done. And we'll have to work that out. That's that's partly a technology issue to make it faster, and partly a user interface issue to figure out what kind of help do you need at what time scale. Okay, and the how. So what is programming? So I asked for a dictionary definition, and it sort of came by as step-by-step instructions. Uh, and that sounds right. And we're used to this idea that you've got to define everything so explicitly, step by step, exactly what to do. And that's what we think of as programming. Here's a programmer. So you might have seen this picture before. This is Margaret Hamilton. Here she is with the stack of assembly language code for the Apollo space mission. She's known as the coiner of the term software engineering. And then, true story, she was actually my boss in my very first job out of college. So how great was that I got that experience. And here she is it looks like she's kind of wrangling that code to make it do everything just right, step by step. And that's what we think of as programming. But on the other hand, if you think of it that way, it seems like a programmer is like a micromanager who's telling you exactly what to do. And nobody likes it when they're told exactly what to do. Darth never won Manager of the Year award. So maybe we want to change that a little bit. Maybe if we don't want a micromanager, what should we think of? Maybe a teacher or a partner or a community of practice. That seems like a more inviting metaphor than the step-by-step micromanager approach. And I think back, so there's this famous software engineering book on design patterns, and they got the idea of patterns from this other famous book on architecture, real architecture, the towns and buildings and construction type of architecture, not the software architecture. And in the original pattern language book by Christopher Alexander and his team, they talk about these, how to make systems of livable communities, right? So this view seems like a good one. There's trees, there's bike paths, there's people eating outside, and that's much more livable than other patterns of building cities where everybody's isolated from each other. And so the way Alexander describes these are with flexible guidelines, not fast rules. And the way you do architecture and the way you build a livable city, you have change and evolution is expected, as opposed to the way we traditionally build software, where we just say everything's completely prescribed. So maybe we want to change that. Now, here's a book by Hansen and Sussman from 2021. So sort of right before we started to get into this AI programming. So there's no AI in this, but they do take this approach of saying this idea of flexibility seems really important. And they say in biological systems, they use contextual signals that are informative rather than imperative. There's no master commander saying what each part must do, right? So in a computer, you have a CPU and you have a program counter, and it says, I'm going to do this step, then this step, then this step, then this step. And everything on the computer, all the peripherals follow that. in a biological systems like ourselves or other animals or plants, there's nothing like that. Rather, there's all the cells communicating with each other and coming up with behaviors based on that. And that means that biological systems are much more flexible, self-repairing. If something goes wrong, they can fix themselves. Something goes wrong with a program, it doesn't usually fix itself. You need somebody to come in from the outside to debug it. So maybe we want our code to be more biological-like. And we want flexible interacting systems, not step-by-step instruction. And we see this in science fiction. So this is a page from TV Tropes, which sort of lists these tropes, these common ideas that show up in television and movies. And in a lot of science fiction, the aliens come in and they have things that they built that look kind of organic. They look like animals that were grown rather than like sheet metal that was designed. And so we've got this idea that there is another possible way to build things, but we don't have good examples of how we've done that here on Earth. Okay, so now in terms of the what. So we started out years ago with assembly language, and we did that because it was good for the CPU. It was efficient. And then we developed high-level languages, because they were good for human programmers. And large language models can learn these languages, but they might not be the best for a human AI partnership. In addition to programming languages, we have all these specialized notations in math and chemistry and music and linguistics and so on. And these are great. And there's power in these languages themselves. And we want our systems to be able to learn from them. Here's a little example. So my friend Wei-Hua Wang said, I have this simple problem. List all the ways in which 3 distinct positive integers have a product of 108. And he asked a bunch of LLMs, and I duplicated what he did, and only 2 of them could get it right. And a lot of them, they made a mistake, right? So they said, the first thing they did was good. They said, let's come up with a prime factorization of 108. And I think it's 2 times 2 times 3 times 3 times 3. And then they said, so I have to take those factors and break them up into 3 distinct piles. But it kind of forgot that 1 is a factor. 1 is a factor of 108. And so it left those out because, it's kind of natural to think of the prime factorization of an integer. And then you kind of have to specially say, well, 1 is sort of an exception. And then I took the same prompt and I said, write a program to do this. And almost all of them got it right. And I think that's because when you write a program, it'd be weird to say for I equals 2 to n, and it'd be normal to say for I equals 1 to n. And so just sort of the idioms makes it easier to do. Here's another example. This is the codex problem where it says, I'm going to solve mathematical or science questions. And the way I'm going to do that is writing a program and then running the program. And I don't necessarily show the program to the user, but I use it as an intermediate step to kind of help me get a good answer. So why does it help? Well, one reason it helps is you can run it and see if there's a runtime error, and you can vote, right? So you could say, I'm going to try to solve the problem 10 times. I'm going to come up with 10 programs, run them all. And if 8 of them get the same answer, that's probably the right answer. I can't do that with natural language. I can't say, I'm going to generate 10 paragraphs of text and then see which ones agree, because they're all different and you can't tell what the final answer is. So using executable language as an intermediate step helps you get the right answer. And so that's the intermediate step. And I think what we want to get to is something like an AI conversation language that are good for human AI partnerships. We want it to keep track of all the relevant information. We want it to have a choice of being precise or vague. So I might want to just say, well, just go ahead and solve this. Or I might want to say, start getting into the step-by-step approach. and I want it to be able to give advice rather than dictate commands. Now, we don't have a language to do that yet. We can use prompts as they are, uh, and we can use programming languages as they are, but we don't have something that combines the best aspects of both of those quite yet. Now, finally, I want to talk about what in terms of the operating system. So we've gone through various phases of operating systems, from mainframes to PCs to now mobile operating systems. Uh, and here's the situation where we're at, right? So you want to do something new, so you take an app, you install it, it comes up with all these privacy type issues of, can I do this and that? Nobody ever reads these things. You just go ahead and use it and hope for the best. Uh, but what I would like to have is have an operating system that consists of a personal assistant. So rather than have all these icons for different apps, I just want to have one thing that I can trust is on my side. I don't want to have to trust all these apps. I want to have one consistent interface the way I like it, rather than have every app have its own interface. I want it to be able to negotiate services for me. So rather than saying, I want a car to show up here, I'm going to press one button for this service, whether it's Uber or whatever. And now I've given complete control of all my information, given up all my privacy to this one company, and I'm hoping for the best. And I kind of believe that this company wants me as a customer, so it wants to do well by me. So that's good. But on the other hand, I know the company's first goal is itself, and serving me is only its secondary goal. And I'd rather have something that I can have more trust in, is really on my side and maintains my privacy for me, learns to work with me. So maybe there will be one app that I feel is mine and I can trust, and then it will go out and interact with everything else, rather than me have to load all these different apps on my phone and hope for the best. Okay. And I got to say, I was at Sun Microsystems when the Java programming language was invented, and that was the original idea for Java. It was to develop a programming language for consumer electronic devices, right? So even way back then, we had this problem of, in your television room, you've got three different remote controls and you're not sure which button to press. And the idea was Java was going to be the language that was going to solve all that for you. Turned out Java evolved to do other things, but that vision of you should have one device, one program that's on your side, I think that's still a good vision, and we may be moving in that direction. Okay, so why don't I stop there and open it up for discussion?
Okay, thank you, Professor, for your great presentation. And I think my dear professor accepted to lead the discussion, and we can have Professor Rohban and question from the audience. Dear Professor, you.
Thank you so much for your nice presentation. I have few questions, but I would rather want to maybe invite other audience to ask their questions, and then I ask my own questions if they don't have any further.
Okay.
So let's see if we have anyone in the room who wants to ask a question. So Arash, yeah, Ali Reza, please go ahead.
Hello, can you hear me, Bill?
Yes.
First of all, thanks for your awesome presentation. I have a question regarding the last topic that you mentioned. This is, I believe, perfect idea to have kind of AI-based operating system. But the things that I have in mind is that it's not kind of possible, at least with the direction that we are currently going, because in language model, each token, when we want to process each token, we have to pass it through multiple layers of transformation, which are uh, heavily resource heavy, and we cannot do it in a single CPU clock or even GPU clock. We have to wait for the entire layers to attend and transform the whole token. My question is, how do you see it when you say we can have a personal AI OS? Because at current time, I believe we should use some other backbone, and AI is kind of just interface. Is it possible to have AI for the whole operating system? Yeah.
Yeah, that's a great question, and I think you're right that we're not ready right now to enact this vision, in part because of software and in part because of hardware, right? So we don't know how to write a whole operating system in this format, uh, and device drivers and things like that. We don't have any confidence that it would get them right. So I think if we do go in this direction in the short run, there's still going to be a bunch of C code or even assembly code that gets called upon at the lowest levels. Uh, so that will have to be figured out, and maybe some way of sandboxing them. So we say we want to be immune from attacks. So if there's untrusted code, maybe some way of dealing with that. So that's part of it. The other part you notice is that particularly, if I've got a mobile device that I'm carrying around with me, right now we don't have the computing power and the battery power to run large language models on that. So that will require some improvements, better battery technology, uh, better GPUs or equivalents, and better software models to figure out how can I condense a model that previously ran in the data center and took a lot of resources into one that can fit in my pocket. And we're a couple generations away from making that work, but it is pretty promising, right? So yes, the best models that are talking about, they do run in the data center and they have a lot of compute power behind them, but much smaller distilled models are almost as good. And so I think we can get to a point, at some point in the future when the hardware gets better and our idea of how to do distillation gets better, where you can do a lot locally, and then if you have good connectivity, the rest of the stuff you can call out to the data center and get a response back. Uh, I think there will be an issue of saying, if I lose that connectivity to the data center, do I feel like I'm really lost out, and it's like I've gone blind, and so we've got to hope that the processing you can do locally is strong enough that maybe it's not quite as good, but it's still a good fallback. So yeah, we're a ways away from instituting this vision, but at least I think we should be thinking about how to move in that direction.
Thank you for that. I have another quick question, which is regarding the point that you said to have some biological inspired softwares. I want to know how we can design, what is in your mind about designing a software which is which kind of the part of software communicate to each other uh, in a manner that we do. We can have errors, but these errors do not accumulate, and there is error correction everywhere. Um, and through AI, how this can happen? This is my another question. I
Yeah,
hope I
yeah.
explained.
I think we need research on that too, right? So we do that at some level in like in our data centers. Uh, so so Google was kind of successful in part because it said, uh, we're going to take advantage of computing on very cheap PCs. So it was a time, uh, in the early 2000s when other companies are saying, well, we're going to build our data center and we have to get the biggest, highest end computers that are really expensive. And Google said, no, we're just going to take cheap off the shelf PCs with regular disks, and we're just going to buy a lot of them, and we're going to expect that lots of them are going to fail. But then we have ways of routing around the failure, of saying, if the server doesn't come back within this number of milliseconds, then we either drop its results if we think it's not important, or we fire up another one and try somewhere else. And then building this reliable system out of unreliable components is something we know how to do. I think, my vision goes a little bit beyond that, right? So that was allowing unreliable components at the level of a sort of large task of, I say, okay, this computer, you're in charge of giving me all the web pages that match this query for the following subset of web pages. And then this other computer, you're doing it on this subset, and so on. And then you do things like saying, all the important pages, they should be on two different computers so that if one of them fails, you still get a good result, and so on. But it's still within each of these computers running a step-by-step program. So I think you start by saying, build a system of communicating processes, and build a system of reliability on top of those. And then over time, you say, now can I go into one of those processes, and then can I break that down into smaller pieces and make them self-correcting? And then, so I think we know how to do that one level at a time, certainly at the top level, maybe at the second level. We don't do it all the way down to the bottom. And I don't know what it will look like if we're going to be able to do that.
Thank you. Thank you for explanation.
I have a question myself. You mentioned that experts like Karpati can know exactly how to communicate with these tools to do their programming. And my question is, if for new programmers, for people that are starting their programming journey in maybe in 2025 and want to do programming, it's very tempting to use large language models to do everything. And how do you think, how much do you think they have to spend on understanding the fundamentals of programming, computer science skills, and how much they have to rely on that? And
Yeah.
if you would start in 2025, how would you navigate that the programming path that you want to be expert on?
Yeah, that's a great question, and we've had this before, right? So I remember when handheld calculators started to get popular, and people said, "Oh, well, students will forget how to do arithmetic, but won't that be bad?" And and I got to say, at one point, I knew how to do square roots by hand. And all I remember now is that it's kind of like long division, but different. But I couldn't do it again now, and I'm perfectly happy to have my computers or my calculators do all my square roots for me. And I don't think I've lost much by not having that. On the other hand, I feel like there are things that I probably should know. Uh, and I already feel, even before AI, I already feel this kind of generational difference, right? So 10 years ago, like I would remember, uh, I'm at work and we want to build something, and there's this new software package that seems to do the right thing. We just learned about it, and I'm with my teammate who's of a younger generation, and we say, great, let's do this. And so I start reading the manual and trying to understand everything about this package. And then, like an hour later, my teammate comes back and says, okay, I'm done. I figured out how to use it. I made this call and that call, and it does the right thing. Now let's move on to the next problem. And I say, oh, wait a minute, but in this package, how does it do such and such? And how does it do this other thing? And they say, oh, I have no idea, right? I learned enough to make it do the two things we needed to do, and it works. So that's all I care about. And I feel like a lot of times they're right. And I was trying to learn something that I didn't really need to know about the details of this package. but sometimes I'm right, and sometimes it really mattered to know those details. And by them going quickly and not figuring that out, that's going to come back to bite us later. And it's really hard, I think, to figure out when you're in which case. When do you really need a deep understanding, and when do you say, this is not the most important thing. I should focus on the important things, and I should just let this go by. Uh, and so I don't know the right answer for that, just in terms of how much do I need to know about this package. And I guess I don't know the right answer in terms of what I need to know about programming. I do feel like if you're going to be a professional programmer, you should know all this stuff, right? You should read Knuth and these other sort of fundamental uh, uh, parts of our field, and you should have a good feeling for them. On the other hand, if you're not a professional, I think it's okay to not know that, right? So I mentioned two examples in the talk. Another one, I have this friend who's a PhD biologist. He studies bird migration, and he said, I'm not a real programmer. I know enough that I can pull some data out of a spreadsheet and I can make a chart to put in my publication. But he said, I always wanted an app that would like visualize the data on bird migrations. And I knew a real programmer could do that, but I never could. And and then I used Copilot and I built the app and it works. Uh, and so I think that's great. And it would have been a waste of his time to become a professional programmer and learn all this stuff. But he learned just enough that he was able to do the thing that he wanted to do. And I think that's fine. Uh, so, there's no one set answer on what you should know, and you can't know everything. We're all given a limited time on Earth, and we got to put that time to the best use.
Okay. Thank you, Professor. So it's very tempting. If you're a new programmer, it's very tempting to not go and learn all the fundamentals. But
Yeah.
but you're saying you have to go about it in a natural way. If you get curious about something, go understand that thing. And
Yeah.
thank you. Let's see other that have questions. Okay.
I just wanted to ask a question. So, that idea of inventing a language which is the right choice for collaboration between AI and human, it's very interesting. So, my question is, what uh, type of properties that language should have, and which roadmap should we take to get to that language? I'm curious to know your opinion on that.
Yeah. Uh, I guess the roadmap I would use is say, let's look at other systems of notation that have been successful, right? And look at their history and look at their current usage, uh, and try to figure out how we got there, right? And I showed some examples of like chemistry notation and music notation and so on. And those all had to be invented. And for most of them, there were like false starts of, we tried something and it was hard to use, and then we came up with another notation. And so I think we want to do that. Uh, and I guess I'm not sure of how much of this is going to be specific to each problem versus how much is general, right? So I want some way which I can say the things I want to say and say it with the right amount of precision. And natural languages have the advantage that they're very general, and you can say almost anything, but they're also imprecise. And so we want some ways to sort of put precision on top of that. And some of that we use with these specialized notations, the notations of math and so on. Some of it, I guess, is going to be a mix of how much is specific to this problem versus how much is general to the field that we're dealing with versus how much is general to problem solving in general, right? And we've seen like these constitutional AI systems, and we've seen these very general prompts where you say things like use step-by-step reasoning, use chain of thought, and that helps. When you put that in the prompt, you get a better result. uh, I think we should figure out which things like that help, and then not have to say them in the prompt, but have the system know that it should do those things. uh, and so maybe they're kind of in the background, and you only have to see them if you're really looking into the details. Uh, and I think having a variety of different ways of thinking about it is really important, right? So I mentioned that there's this controversy uh, uh, over models of, of other beings, and there's also this controversy over, can large language models be creative, and what does being creative even mean? And I think part of it is having the right components and being able to put them together. Uh, One thing that struck me is so we have this AI reading group at work, and somebody was presenting a paper, and it says, here's this model, and it's got these matrix multiplies, and then this is equal to this as a theorem. And the presenter said, this theorem looks right, but I couldn't quite work out the proof. And then one of the people in the audience says, oh, the proof's not obvious because you're using the wrong notation. He says, I'm a physicist, and physicists have this different notation for writing matrices. And so here, I'll rewrite this formula using my notation, and now the proof is just this cancels with this, and it's like a one-step proof, right? So the fact that he had that notation meant he could solve problems that we couldn't. And I think I want a language that allows that to happen quickly and freely. And I think that's hard in our current languages, right? So, like in our current programming languages, we have different ways to implement like a set. You can implement a set as a hash table or a tree or something. Uh, and there's advantages to using each one, but it's not fluid in that, if you wanted to switch between the two notations, you'd have to explicitly say that. And, here I'm representing this set using this notation, here I'm using this other one. Uh, and I'd rather have an approach where you didn't have to do things like that, where you could say, what I want, and then kind of, if you look under the hood, then it says, here's how the implementation goes, and here I'm making all these choices, and I don't have to worry about that. So there was this idea about 20 years ago, maybe more, called aspect-oriented programming. And that was the idea of, when you're programming, you're worried about different aspects of the problem, uh, but we put them all together into one long piece of code. And maybe it'd be better if you could break them up, right? So, one aspect would be, what's the security of this system? How do I know it's safe? And wouldn't it be nice if you didn't have to make the code twice as long because you're worried about that? You just have the code that says, here's basically what it does. And then off to the side, you say, oh, and by the way, here's how we make sure that it's secure, or, all these other aspects of it. Uh, and so I think that was a step in the right direction. So can we break things up to say, I want to talk about the things I want to talk about in the order I want to talk about it, and I can ignore them if I want to, and I can bring them back to the forefront if I want to, rather than having something where every single step has to be entwined into the code, and can't be moved or changed because it's all happens at the same time. So I know that sounds vague, and I don't have the answer. If I did, I'd be off and doing that, and I wouldn't be talking to you guys. Uh, but these are just some thoughts as to how to go in that direction.
Right. So is the pseudocode that we usually take advantage to uh, transfer the knowledge of some algorithm to other people in high level in different abstraction levels, is that something close to what you
Yeah,
mean for
I
this
think
purpose?
so. I think so, and I think so Python's now our most successful language, and I think part of that is because it looks so much like pseudocode more than any other language, and so I have experience with that. Uh, so you mentioned that you guys use my textbook. Thank you for that. Appreciate it. And the first edition came out in 1995, and at that point, Lisp was the main language for artificial intelligence. And we said, we want the book to have pseudocode because we don't want to impose any language on any student or teacher. But in the online site, we had Lisp implementations of every algorithm in the book. And for the first few years, that was good because most students who took the course used Lisp and were familiar with it. But over time, fewer students did that. And we got more and more complaints of, I don't understand the Lisp code. It's confusing. A certain number of left parentheses forces somebody's brain to turn off, I think. Uh, and so I said, okay, I got to choose another language. And first I said, Java seems like the most popular language. I can do that. But Java was what you had to write for Java was so far removed from the pseudocode that I said, that's not working. So I said, is there a better language? And I didn't know that much about Python. I sort of knew it existed, but hadn't used it. And so I started looking into different languages and then I said, wait a minute, Python, Guido van Rossum, he chose a language that's almost exactly the same as the pseudocode we invented for our book. It's like we were in a mind meld. So I said, this is easy. It's the simplest language to implement the pseudocode in the book because it's almost word for word. Uh, and I think that makes a big difference. I think that's why Python has been successful. And and I think we should do more of that, right? And and also there's lots of things you want to be able to say that you can't say, in Python. And I remember, having some conversations with non-programmers and having them say, "Well, why don't you just say like you can never do X?" And I said, "Well, yeah, that's a great idea. And if we were programming constraint logic programming, I could say that. But in regular programs, you can't say you never do X. Rather, you have to look through the program, find out every place where X might happen, and put in code there to never do X. Uh, and having the non-programmer say, "Oh, that's just silly. Why can't I say what I want to say?" Uh, and and then realizing, we built the system where we even forgot how silly it is, right? We forgot that uh, there are simple, obvious things you want to be able to say that you just can't say because you have to describe it in this algorithmic way. And so maybe taking some time back to say, what are the kinds of things you want to be able to say, and then making it possible to say that.
Great. I have one more question regarding the fact that nowadays LLMs help a lot of people write programs in much shorter amount of time and in much more convenient way. Uh, the problem is that once those programs are implemented and developed, they may not pass the unit tests that verify their correctness. And in those cases, if somebody already knows the programming, they can go through the program and try to fix it and try to figure out, which lines are incorrect and causing the program not to run correctly. Uh, but for non-programmers or non-users, as you mentioned, this is impossible. And in a lot of cases, we know that LLM itself cannot find those bugs easily, and that would be a simple kind of like a dead end for the user.
Yeah.
So how do you think that may change in future?
Yeah. So one thing is, I think they'll just get better, right? So I showed a bunch of examples where I said a year ago they couldn't do it. This year they can. And so next year they'll be even better. Uh, I also feel like, well, we're used to this idea, right? So, you know, if something goes wrong, say with my plumbing, if it's a simple problem, sometimes I can fix it. I have a set of tools and wrenches and so on, and there's some things I can do. But then there's other times when I just say, I can't figure this out. I got to call a plumber, and they've got the expertise and they can do it. And so I think we're used to this idea that there should be some things that you, as a naive person, can solve on your own, and maybe you'll get better over time. And then there are other things that you really have to call in the expert to do. Uh, so I think that's okay if that still happens with programming. Uh, I think we want to make it so that that happens less often, and it's easier for you as a non-programmer to fix things. And so having this language of dialogue, I think, is part of that. And and sometimes it works, and sometimes it doesn't. I think, I guess another aspect that I think is important is bringing everything of the software process kind of under program control. And we don't do that now, even as professional programmers. So I've seen so many times when, here's one example of, uh, so you're inventing a new product and you hire the user experience experts to say what should be like. And they do a bunch of tests, and they bring people into the lab and they try out some paper prototypes, and then they implement some prototypes, and then they try it and they say, out of everything we tried, here's the best user interface. And you say, great, that was a fantastic report you wrote. We're going to pass this off to the engineers. They're going to implement it. Our users are going to love it. And oftentimes that works great. But then maybe a year or two later, the world changed in some ways. Maybe people are using devices that are of a different size than you designed it for. And there were kind of implicit assumptions in that report that was written that are now violated. But the only way you'd recognize that is if somebody remembers, hey, remember that PDF report that we saw 2 years ago? I think we should revisit that. I think there's something has changed, and maybe we want to think about changing the user experience in some ways. But it's not part of the program, right? The program doesn't know what the report was. It doesn't know what the assumptions were that led to this particular UI being chosen. It's just not, it's off on the shelf somewhere, and we rely on the collective experience to remember that. And if it was part of, sort of part of the executable of the program, then maybe it could automatically fix itself, or maybe at least it could say, hey, assumption has been violated. Uh, you know, we did this under the assumption of such and such. That's no longer true. What do you want me to do about it? You know, so one of the ways I think about it is, the great thing about these neural net models is they're differentiable. You run through them, you get some output at the end. If that output is not the right answer, you can differentiate back and change it. But if your whole software flow has a bunch of stuff and some documentations and some tests and some code, and then a tiny little bit with a neural net, and then maybe some output, and you can only differentiate through that tiny little bit, then you're missing a lot. I want to be able to differentiate through the whole software flow to say, if something goes wrong anywhere, I want to be able to recognize that and make a change, maybe automatically, or maybe just alert that something has to be looked at.
I see. So I was thinking maybe if that language that you mentioned that is a better choice for collaboration between human and AI is invented, that may also help in situations like that. Isn't it the case?
Yeah, I think so. Yeah, yeah. I think you want sort of these reports to be written in a kind of semi-formal format that can be used for this, and I see examples of this. So DeepMind just announced this week uh, a bunch of formalization of mathematical problems, right? So they're problems that are well known to mathematicians that are kind of stated in a combination of natural language and mathematical notations. And what DeepMind said is, we've now formalized them in the format, I think it is of this theorem prover called Lean, that has a formal language. So we can now say, here's this informal statement of a mathematical problem. If you're a mathematician, you kind of know what it meant, uh, but it was imprecise. And they said, now we have precise definitions. And so now if you want to, test, I have my mathematical problem solver. Now there's a whole database of tests where you can tell definitively, am I right or am I wrong? Whereas before it was like, oh, hey, my solver solved this particular problem, but maybe your formulation of it wasn't quite the same as what mathematicians accepted. So having this kind of formalization, I think, will really help the field advance in the same way that having ImageNet helped the field of computer vision, where previously there were only thousands of images available, and ImageNet said, no, if we're going to make progress, we need many millions of labeled images, and that's going to be a big task to create. But once we create it, the whole field can move forward.
Great, thank you. I have no more questions. Let's see if there is any other question from the audience.
Yeah, I see a hand up.
So Arash, can you take care of those?
Sure. I have a question. A few months ago, for our first guest lecture, we have Rich Sutton, and I remember in his first few slides, he mentioned that the important role that your textbook played uh, uh, in emphasizing the view of agentic view in the whole field.
Mhm.
I was, as you were talking, I was wondering to ask you what was the reasoning behind that in 1995. I don't think it was something that was everybody doing or everybody talking about. What was the reasoning behind it, and how do you decide that you uh, design your whole book about the agentic view about the AI?
Yeah, so great idea. So first of all, it was awesome that you were able to get Rich to talk with you. You know,
It
his
was
book
an
his book also very influential to the field, and actually I have right here this month's communications of the ACM, and he and Andy are on that. Yeah. So how do we go about writing the book? So it was, I guess, 1993. Maybe no. I guess we first started talking about it probably in 91 or 92, uh, and so I was at Berkeley, and the AI faculty there would go out to lunch, and we'd say, the AI textbooks that we all learned on, that we certainly appreciated, from giants of the field like Pat Winston and Niels Nielsen and so on. Those were great books in their time, but it felt like the field was changing in several ways. So, so what ways? So, first, in the early days of AI, it was kind of focused on this idea of expert systems, and the idea that you go out and interview an expert like a doctor and say, well, how do you diagnose this case? And then you try to build a system that duplicates that reasoning. Uh, and then it felt like the field was moving more from expert systems to normative systems that said, I want to make decisions that maximize expected utility. And I'm not going to tell you how to do it. I'm just going to tell you what it is you're aiming at. And then also there was a move from logic to say most of AI should be about logic with maybe some non-monotonic type stuff thrown on, to saying, no, that was the wrong way to do it. Probabilities are really the right way to think about it. That in some ways, the defining aspect of AI is that it's about dealing with uncertainty, right? And I kind of feel like, if you say what's AI about, it's writing smart programs that do the right thing. Well, how is that different than software engineering? Because software engineering is also writing programs that do the right thing. And to me, the difference is in software engineering, the enemy is complexity. That it's hard to write the software for a bank because there's a million different transaction fees and taxes and so on. You got to get everyone right, but there is an answer down to the cent of what the right answer is. And whereas in AI, typical problem is here's a photo, what's in it, and you have to say, is that a wolf or a husky dog? Well, it's kind of hard to say. Maybe there is no definitive answer. It's dealing with uncertainty. And so that hadn't been highlighted as much in the previous book. So we felt it was normative systems, dealing with uncertainty, and machine learning rather than hand coding. We thought that was all important. And then we said, well, what is it we're trying to do? We're trying to make systems that make good decisions so that they can take correct action. And to me, that was fundamental to the field, and my co-author Stuart Russell agreed. And it really goes back to the invention of the field with Alan Turing and with his Turing test, right? And the test comes across as saying, well, it's about, can a computer talk to you in natural language and be indistinguishable from a person? But I kind of felt like, of course, I never got a chance to meet Turing, so I don't know what he really was talking about. But in my interpretation, it wasn't that important that the task was tricking someone into thinking that you're human. What was important was that there was a task and there was a pass-fail test. And I think he was really reacting to philosophers who said, oh no, just on first principles, AI is impossible. And I think what he was saying, well, let's leave the philosophers out of it and let's just say, let's define a specific metric. And if you can meet that metric, then you've solved the problem. And so we said, that's how we want to talk about AI. And so we talk about it as taking actions and taking the right action rather than the wrong action. And so we thought that made sense, that the field was changing. I think, it was just sort of luck that we came along at exactly the right time where all these things were changing, and we wrote the book. And then I don't know if it was good luck or bad luck, but everybody else said, oh, well, your book is good enough, so we're not going to write another one. And so we've had to keep writing updates over 30 years now.
Thank you for that. Thank you for a great book. I think it shaped our view about AI, many of us that are starting the field. I have, if audience don't have any question, I have another question.
Well, let me just say one more thing about the book. So, when we started, Stuart and I felt like we had similar views of how the field works. But I think one thing that really made the book come together is that we didn't know when we started is that we have very similar writing styles. Uh, so we try to throw in a little bit of humor in the book, and I think we both have similar sense of humors, and just in terms of sentence structure and so on. So I remember, in the early days, we'd each write a chapter, then we pass it back and forth, and he would make changes and pass it back to me, and I would make changes. And I remember reading a draft section and saying, oh, this is pretty good. I bet I wrote this. And then seeing that like the word behavior was in that paragraph spelled with an extra U in the British way, and saying, oh no, I guess I didn't write this. I guess Stuart wrote this, but I can't tell the difference. And I think that really helped, that some co-authored books, there's kind of a clash of styles that holds it back. And we were lucky that our styles were very similar.
Thank,
But your next question.
thank you for mentioning that story. It was very inspiring. Okay, my question is, what do you think about this current wave of AI? Basically, what we are doing right now is make giant prediction machines and do some reinforcement learning on top of it, and maybe help it to do some search and reasoning, and maybe explore a little bit more in the knowledge that it got. And the current wave also, we get it a little further. We made some different experts that they can communicate to each other, and they can solve big problems that no any one of them cannot solve. My question is, what do you think when do you think this current wave of AI would plateau? And do you think there are fundamental things in the way that natural intelligence works? Is there something fundamentals that we know from neuroscience, cognitive science, that is missing in the way that we build intelligence systems today? And how can we go about it to see 20 years, 30 years into the future? Maybe there's the next winter coming in 5 years.
Yeah.
What should we expect?
I think it's hard for anybody to see 30 years in the future. Certainly, don't trust me. I don't have a good record for predicting that far into the future. I guess I'm pretty happy with where we are and with this idea of prediction. I think, a lot of how life works, how evolution works, I think really is based on this idea of predicting and then correcting failure. So to me, that makes a lot of sense. Um, I do think it was important for us to do all this stuff that you sort of glossed over as saying, well, we added on, right? So certainly, and we use this word language model, and I think sometimes we forget exactly what it means, right? Because the language model does have a very specific technical term, which is the probability distribution of the next word given the prefix of words, right? That's what we mean by language model. And if you only use that, that doesn't seem very intelligent, right? If I just say, I'm going to give you a prompt, now you spit out the most probable next word, and then I feed that back in, and you spit out the next word, and so on. That doesn't really seem like intelligence. That, Emily Bender uses this word stochastic parrot. That does feel like a stochastic parrot. Or, I say, well, it feels more like an artificial politician than an artificial intelligence. So politicians are good at just talking and spitting out one word after the other. In order to get an artificial intelligence, you have to go beyond that. And I think the models we currently have do go beyond that, right? So they don't just say, oh, what's the next most probable word? I'll spit that out. Rather, they say, let me think about that problem. Let me simulate out, and maybe I'll try doing that 10 times, and then I'll compare the outputs, and I'll criticize them, and I'll vote, and I'll do all these things, and only when I've done all that reasoning, now I'll start talking. That feels a lot more like intelligence. So I kind of feel like we're on the right track. Now, there's this big discussion of when are we going to get AGI? I would rather that discussion go away, and I don't think that it's kind of binary, that there's only one, either you're there or you're not. But I wrote this piece with Blaise Aguirre of saying, well, in one sense, AGI is already here, in that we've changed from writing programs that were specific, right? So one program that can only play chess, one that can only play Go, one that can only do speech recognition, to writing programs that are general, that can do lots of things. And that is new. And this is the first time we've had that. And my analogy is, in 1945, we got the ENIAC computer, which was the first electronic general purpose computer. And it was general in the sense that it was Turing complete, right? So it had loops and conditionals, and it was programmable. So in theory, you could program anything on it. In reality, it was too small and too slow to do almost anything useful. Uh, and it was a terrible computer by today's standards. But in terms of generality, it achieved 100% generality. And so I feel like today's language models, they've achieved 100% generality in that they can do lots of different things. Now, they fail, right? So they're not perfect in the sense that they can do everything that a human can do or that a superhuman can do. But the way we deal with them is general, and that's something new that we didn't have before. So I think that's important. And where are we going to be in the future? Uh, I think we'll still have this idea of prediction. So, I don't know exactly what Richard Sutton said, but probably the things that he said, we're going to keep those kinds of ideas, right? We're still going to be predicting. We're still going to have feedback and improvement. Now, everything else may change. So we kind of hit on the transformer model for LLMs, and a lot of people do that. I think that was kind of accidental, and I think part of it was, why did we choose transformer the way we did? Part because the NVIDIA chips we have certain strengths, and we wanted an algorithm that took advantage of those strengths. And if we had different chips, we'd probably have a slightly different algorithm. But it would still have some notion of attention, some idea of saying, I want to remember some stuff from the past, but I don't want to have to remember everything from the past. And so these broad aspects, I think, are going to follow through. But, probably in 5 years, none of the code that we have today will still be there. It'll all be replaced, and maybe there'll be a different name, and maybe they won't call it transformers, and maybe all the little components will change. But I think the large structure of dealing with a lot of data, correcting your errors and improving, and using these multi-step reasoning, I think those ideas will persist.
Thank you, Professor. Do you think there are fundamental ideas that are missing, or maybe fundamental components that are not emphasized in these systems that we have to go back and think about them? Do you think there are some things that we have to?
I guess the biggest thing for me is uh, figuring out the right kind of learning loop, right? And so part of the problem we're facing is these models are big and it's expensive to train a new one. And so we kind of have two ways around that, right? So we have this idea of fine tuning, that you take an existing model uh, and add to it and make small updates to the weights. We also have this idea of distillation, that you take a model and you make it smaller by kind of compressing those weights. And then we have the idea of a context window, and we build larger and larger context windows so that it can remember kind of the local stuff. But I think one of the big weaknesses is once you quit, that context window goes away, and we haven't learned from that. And that's just sort of the architecture, that it's just expensive to retrain and update, and maybe we're also worried about poisoning of attacks, or we're worried about leaking of privacy. And so I think we're not taking advantage of sort of that loop and doing immediate feedback, right? So we update in large steps. You see, uh, Chat GPT is at version 4.0 or whatever it's at, right? And I'd rather it be at version 10,000. Yeah, and saying, we update continuously and we keep on making it better based on the interaction with the users. But because of the way the current architecture is, and because of the cost of computing and so on, we aren't doing that. We aren't making those frequent updates. We aren't taking as much advantage of the user's information as we have. Instead, we're trying to force that all into the context window. And I wish we could break that bottleneck.
Great, and thank you for your answer, Professor. Let's see if the audience has other question. Then I can ask the final question. We have a few minutes. We have a question.
Um, Hello, Professor. Thank you for your talk. I had a questions about the interpretability of these large language models. Like one of the things that they mainly mentions that these LLMs are some kind of how a black box. Like we don't know how exactly and precisely they are generating what they generate. Do you think this as an issue, and like do you think that if we make them more interpretable, can we make them better, or like what's your opinion on that?
Yeah, I get, so people talk about uh, interpretability and explainability. Uh, I think those are important. I think they're mostly important in a secondary way, in that what's most important is trustability, right? So I want a system I can trust, and explanations are one way to do that. So explanations when you ask the system and it gives an explanation. Interpretability is when you look inside the system and open up the black box. And so both of those help to build trust. But I think there are other methods as well. So auditability, I think, is important, and in some cases, it's maybe more important, right? And uh, like the European Union really focused on explainability, and they put in a law that says an automated system that makes some decision on your behalf, you have to be able to ask for an explanation, right? So if I go to a bank and I apply for a loan and it says no, I have to be able to ask for an explanation. And so maybe it says, your credit score was too low, or you didn't have enough collateral, or something like that. So it's good to have that explanation. But, let's say I'm worried that it's biased against me in some way. It doesn't like my sex or religion or race or something. If I ask for an explanation, I can't tell if it's biased. The only way I can tell if it's biased is to do an audit that says, well, forget my case for the minute. Let's look for all the cases of people that are in my class versus people that are in another class, and what's the approval rate for each of those. And if I have that answer, then I can say, oh, look, you're biased. I can't have that just from the explanation. So, explanations are kind of limited. And also I feel like we fool ourselves too much, right? And so, every day the stock market goes up or down, the weather is rainy or shiny, the sports team wins or loses, and there's an expert on that explains why that happened. But if it went the other way, they'd have an equally plausible sounding explanation. And so maybe we put too much trust in these explanations, and I'd rather have more sort of tests that you can't cheat on, or something in addition to those explanations. Now, in terms of the interpretability, being able to look from the outside into systems, I think that's really interesting. And Anthropic had a recent report out that I think is really interesting, in that it sort of looked at what are the types of concepts that the Claude model is learning by saying, we'll feed it some text and we'll say which concepts light up and so on. Just sort of get a gross idea of the kinds of things that are going on. Of course, you can't understand every single concept that it has, so you're limited in what it can do. One thing I think is really cool is, when DeepMind did the original Go playing program, They hired a lot of Go experts and tried to understand what they knew. Uh, and then they said, well, now let's do AlphaGo 0 with no experts whatsoever, just learns from self-play. And now they did that, and that was successful. It was better than any human at Go or chess. And now they're bringing the experts back and asking them, can you explain what the system has learned, right? So AlphaGo got a lot of credit for this famous move called move number 37. And all the analysts said, oh, this is a very creative move. A normal Go player wouldn't have thought of that move, but it was the right move in this situation. But if you can't really ask AlphaGo, why'd you make that move? It doesn't have an explanation for it. And you can't ask, what's the general concept behind that move, right? So it can say, for this board position, this is the best move, but it can't say, what's the general strategy? And so now they're hiring humans to come in and say, okay, this system made this move. Can you understand what's the strategy? Can I teach this to a human? Can I explain why it made that move? The system itself can't do that, but the human experts are coming in and trying to kind of reverse engineer it and make sense out of it. And so maybe we're going to need partnerships like that, where the system itself doesn't really understand everything about what it's doing, but the system in conjunction with some human experts may have better insight into what's going on.
Okay, thank you.
Thank you, Professor. I think we're out of time. Just for the final question, I want to ask if you have these curiosities about intelligence and you want to start in 2025, what path would you take? What do you go on major on? What courses do you take? What books do you read? What is your path if you are curious about the intelligence and you want to be the the researchers and you want to crack the code of intelligence and be the researchers that have something to say in maybe 20, 30 years in the future? What path would
Yeah, great question. I guess I would say uh, look at what problems can you solve. Uh, and I think maybe in the future, uh, you know, so I've had a great career in computer science, and I came along at a time in which it made sense to do that. And kind of the field was just getting going. But I think in the future, it might be more kind of a combination of computer science and AI ways of thinking about things combined with something else, right? And so, I kind of feel like if I was just getting started today, I might focus on medicine and biology, right? Because that seems really fascinating. And, I would say, I want to know enough about AI and computing to be able to apply them as tools to this specific problem. And to me, that's an exciting problem. It's one that affects everybody and one that it feels like we have the tools to do something interesting. And so that might be what I would do if I was starting today. But, if you're interested in something else, then you should do that. And I think maybe say, don't focus only on computing and AI, focus on some application of it to some problem you want to solve, and just start doing those problems and solving those problems. And then, along the way, you'll find the things that you want to read. But I would say go out and try to do something first, and then sort of read just in time when there's something you need to know, rather than study first and do later.
okay? Thank you, Professor. I think it was a great answer. And with that, I think we can finish off the talk if there is no comment. Okay.
All
Uh,
right.
okay. So thank you, Professor. It was truly an honor to have you with us. And I think I hope you have a great rest of the day.
Yeah, thank you. It's a pleasure being here. I appreciate it.
Thank
Thank you.
thank you.
Bye.